In this video, we're going to be working on another set of problems from POD 9, and this problem involves drawing Lewis structures and ultimately figuring out the intermolecular forces. So we'll use that to answer the final question in part C there. Now, the first part is draw a reasonable Lewis structure for these and determine the polarity. So again, the way we go about doing this is you just follow the octet rule for these two compounds. So carbon has 4 valence electrons around it. There are 4 hydrogens, and each hydrogen has 1 valence electron. So you just draw your bonds in between. So I'll just do it here. There's one, there's one, there's one, and then there's the last one. Now, NH3 is, the nitrogen has 5 valence electrons, and the hydrogens are going to go around it in such manner to where they have their single bonds. And then you have this lone pair on top here. Now, polarity is just dealing with asymmetrical versus symmetrical. Symmetrical meaning that it is consistent the whole way around. Asymmetry just means that there's something different that causes a difference, and that's really where your polar compounds and molecules come from, are those asymmetric features that show up. So CH4 is symmetrical, it's all the way consistent all the way around, it's tetrahedral, it's going to be nonpolar. For NH3, you have this lone pair, and normally a rule of thumb is if you have a lone pair, you're going to have a polar compound. So this is going to be polar. Now, that helps us in determining the answer for part B, which is determining the intermolecular forces of attraction. So the first one, which is CH4, it's London dispersion. That's all it is because it's nonpolar. But for NH3, it's London dispersion. And it'll also be dipole-dipole because it has a polar bond. Alright, it's just a polar molecule. So if we pay attention to the definition of hydrogen bonding, it's got a nitrogen that's covalently bonded to a hydrogen, so therefore it also experiences H bonding. Now, these two molecules are very similar in size and shape, but there's a huge difference in the type of intermolecular force of attraction. The molecule for it, the NH3 molecule, has hydrogen bonding, which again is one of the strongest intermolecular forces. And so since the sizes are fairly the same, NH3 should have a higher boiling point and melting point. So as we look at the last question here, it says the molar mass CH4 are nearly identical. Rationalize why the melting points and boiling points are higher for NH3 than those of CH4. Well, again, it goes back to the fact that they're both relatively the same in size, so you have to focus on the intermolecular forces specifically. In this case, NH3 has more intermolecular force of attraction on top of the fact it has hydrogen bonding, and that's what's going to create the much stronger intermolecular force of attraction for NH3 and giving it a higher boiling point and melting point. So that is for POD 9 problem 3.